So. Ja, genau. Also ich werde heute sprechen über Machine Learning in Health, Production Ready Solutions to Real-Life Problems. Und dazu werde ich eine kurze Einführung geben, was die PSIORI ist, was wir tun. Dann werde ich kurz einiges zu Machine Learning und AI sagen und dann Beispiele für reale Projekte bringen und mit einer kurzen Zusammenfassung schließen. Genau, wer sind wir? PSIORI wurde gegründet 2014 in Freiburg, dort ist auch unser Hauptquartier bis heute. Wir haben weitere Büros in Hamburg, Frankfurt und Wilhelmshaven. Es gibt auch Kollegen, die auch noch in anderen Städten sitzen. Was tun wir? Wir decken ab eigentlich die gesamte Entwicklung eines Projekts von der Ideenfindung gemeinsam mit dem Kunden, zum Beispiel in solchen Tröffelhand-Workshops, über das Projekt selber. Oft oder manchmal starten wir mit einem Proof of Concept bis hin zu produktiv einsetzbarer Software mit eben dem Machine Learning-Anteil. Und dabei ist es oft so, wenn wir den Proof of Concept machen, dass das konkrete Projekt, die konkrete Idee, wird tatsächlich nicht so viel zu finden und tatsächlich manchmal eine kleine Erfindung machen müssen an der Stelle. Also oft Dinge, die wir zum Beispiel in einem anderen Bereich angewendet haben, in eine neue Domäne zu übertragen. Das ist eine Sache, da werde ich auch nachher nochmal drauf zurückkommen. Wir decken auch in einer anderen Dimension sozusagen den gesamten Verlauf ab. Wenn man Data Science macht, wenn man datengetriebene Projekte entwickelt, gibt es ja verschiedene Dinge, die man da, verschiedene Stufen der Datenanalyse. Natürlich muss man hier auch sagen, die Daten, die Grundlage sind eigentlich das Allerwichtigste. Das steht jetzt nicht hier, aber wir fangen auch an mit Data Engineering, Datenvorbereitung, so dass man darauf überhaupt Analysen machen kann. Und dann setzen wir darauf eben auf Data Analytics, reinschauen in die Daten, schauen, was ist da, was für Schlüsse kann man daraus ziehen, welche Daten enthalten Informationen, wo ist Neues. Darauf aufsetzen kann man Vorhersagen machen, einsetzbar in den verschiedensten Bereichen. Das kann zum Beispiel in Predictive Maintenance Kontexten und anderen eingesetzt werden, bis hin zur Automatisierung tatsächlich. Da werde ich in unseren Projektbeispielen auch noch ein Beispiel für machen. Genau, ja, was tun wir? Das habe ich gerade schon gesagt, Industrial Automation ist ein großer Bereich, in dem wir arbeiten. Der andere Bereich ist der Health-Bereich, über den ich heute sprechen werde. Wir haben aber durchaus auch noch andere Projekte in anderen Bereichen. Das sieht man auch so ein bisschen hier. Hier ist eine Auswahl unserer Kunden. Viele verschiedene Bereiche, teils Industrie, teils Health-Bereich, aber auch Automotives und andere. Genau, Machine Learning und AI. Was ist das eigentlich? Wir werden heute über Machine Learning sprechen, aber Machine Learning ist eigentlich nur ein kleiner Teil des Bereichs der AI. Allerdings ist es der Teil, aus dem in den letzten Jahren die meisten Entwicklungen kamen, die tatsächlich viele Anwendungen revolutioniert haben und die dazu geführt haben, dass der Begriff AI wieder in aller Munde ist. Es gibt darüber hinaus viele andere Bereiche der AI. Einiges von denen wird Ihnen was sagen. Natural Language Processing ist vorhin in der Einleitung auch schon mal gefallen, ist auch ein Bereich der AI. Es gibt andere Bereiche, Perception-Bereich zum Beispiel, ganz klassische Computer Vision, ist auch im Bereich der AI. Aber wir wollen heute über Machine Learning reden und ein wichtiger Teil des Machine Learning, eben auch der Teil, der jetzt in den letzten Jahren zu den größten Entwicklungen geführt hat, ist der Bereich des Deep Learning. Ich glaube, es ist aber auch wichtig, hier nochmal zu betonen, dass klar, Machine Learning hat die AI vorwärts getrieben, speziell Deep Learning hat jetzt die AI vorwärts getrieben, ist dementsprechend auch ein wichtiger Bestandteil von dem, was wir tun. Aber es ist nicht so, dass damit zum Beispiel die Methoden des klassischen Machine Learnings oder andere Bereiche der künstlichen Intelligenz überflüssig gemacht werden würden. Im Gegenteil, auch da, es gibt einfach viele Problemstellungen, die damit sehr gut lösbar sind und da sollte man das auch weiterhin anwenden.
Es ist eine Frage im Chat, ob du auf Englisch umschalten könntest. Sollen wir es Englisch machen?
Yeah, I could.
Okay.
So I would continue in English. Right. So just let me repeat the takeaways. So AI is definitely more than machine learning, even though machine learning was the part of AI that drove development in the last years, and especially deep learning was the part of AI that drove development in the last years. But it's definitely the case that there are still lots of applications that can be solved with classical machine learning or other parts of AI. And such, they shouldn't be forgotten and should also be still applied there. Right, so one important part of what we are doing, this is using deep neural networks for dimensionality reduction. This is something that, as you can see here, is something that we will see in the most different contexts all over again. I have an example of data from a water turbine where we have two different devices, and here one parameter visualized on the upper left. We have on the upper right already data from the health domain, human genome data that is visualized in 2D. And as we can see, there are separations of cells that contain different mutations in different kinds of cancers. So we can separate the different cancers in this visualization. We have as well fast-moving consumer goods. That's about everything that can be found in a supermarket. This can be clustered, as we can see here on the lower left. Also in 2D representation, we have done such dimensionality reduction. We have learned such a representation on data from a combustion engine. What is quite interesting here is that those were two cars, and what we were actually searching for were points in time where there were fails to start. But what we also saw in the data is that we can distinguish the cars already, although our customer was pretty sure that we wouldn't be able to distinguish them. In the middle, we see customer data. This is like click data from customers of a retailer, online retailer, two different data sets that we put into one representation, and by that make them comparable and see that here in this part they intersect and overlap, and we can see similarities from the click profiles that wouldn't be able to see in any way by looking on the data set separately. So this is something that a method that we have employed in the most different contexts. And from that have derived the idea for a product for the PSIORI's visualizer that we can use for a 3D visualization, and that has exactly this aim to be able to look into your data, walk through it, look at it from all sides, zoom in, and identify interesting parts of your data, interesting KPIs, by also applying your own KPIs as a color map on this data. Here we see one example that we've used. This is again a genome data set that contains about 60,000 different mutations. So very large database, something that can't be looked at just by looking at the table. So we reduced those 60,000 dimensions to 3 here, and we see that the different cancer types are very distinguishable in here. And something like this can be used, for example, to look at healthy persons that share mutations and see where their data point would land in this point cloud, and does it interact with some of the cancerous cells, or doesn't it? So to see if, for example, there is some checkups needed. Another thing that we always continue to see is time series data. So there are lots of different applications where we see time series data. That might be like the example that is shown here, data of, again, a combustion engine. It might be data from sensors of an industrial production park. It might be, for example, ECG data. So time series is something that we always look at. This is the data browser that allows you to browse through this data and especially makes labeling easy. I mean, we will be talking about machine learning, or we are talking about machine learning. That means that we need data that we need to make some sense of the data. We need something, oftentimes we need something, some targets. What are we going to learn? And this is one possibility to label data. When we see, okay, there's a long time series, you don't have to scroll through everything and look through everything by hand. But here we have employed a model that helps you to find similar parts of the data. So if you have something where you say, okay, this is a positive label, this is something you want to find, you can give it to the model, and the model will show you this is similar point, this point is similar, this point is similar. So you can easily label, and the same thing for, oh, this is an outlier, this is something I want to know if there's something like that again in the data. And also our model will tell you, okay, there might be a similar in the similar section in this data, or there might not. Also, time series data, we will have a lot in the health examples later on. So a few words to the three parts of our work that I mentioned before. The biggest single project that we have is actually from the industrial automation part. It's automating a crane with the aim that end of this year, this crane is able to navigate on its own, pick up a load of wood from a truck and deposit it either on a belt or on some pile of wood without anyone actually controlling the crane, a part of our AI. Right, so the next project is one I will go in depth into later on. This is a support for doctors to detect arrhythmia, atrial fibrillation especially. And this is an example for a project that comes from the everything else department. This is an artificial intelligence that that helps the operator for e-mobility charging devices to see if a device is already failing or will be failing in the future by predictive maintenance. That actually looks at all the data that comes in from this device. And the especially interesting thing here is that most of those charging devices are not equipped with sensors like industrial production devices, but more like not so much sensors, but just some signals like your usual IoT device. So this is doing predictive maintenance on in an IoT-like setting. Right. So let's come to the examples for our actual projects from the health department. Right, the first example is actually an example on how to provide data for machine learning, because oftentimes data is not readily available. And this is the very special section, the section of medical study data, medical register data. This is data that actually needs to be regularly analyzed by the companies holding them, the pharmaceuticals. So it already is analyzed, but it's also a great source for ideas and hypotheses for new studies or other ideas if it is ready available for explorative analysis. And often it's not, because there are established processes for the required analysis. Of course, there need to be. There are data standards and requirements that render some off-the-shelf solutions for data holding unusable, because it needs to adhere to the standards. And also often the data is just available for the analysis that needs to be done, and nobody actually, it's not thought about the rest. Our solution together with our customer was to build a data pipeline that's based on the CDISC format. I don't know who knows this. It's a standard format for medical study data. That's not only just one data format, but it's a whole set of data formats and exchange formats that are used for the required analysis of this kind of data. So it's very important that this that any solution holds onto this. So we've built a data pipeline based on this CDISC formats and an easy-to-use front end for simple and standard analysis, what makes the everyday stuff easier and also helps to develop ideas. We have also all this, what's also important, all of this data is accessible in raw form and in any processed CDISC format form. So the established processes can just be kept like they are and doesn't interfere with that. Right, so let's say something about this data pipeline. I already said it's built on based on those CDISC formats. Data is mostly in some long form tables as a raw steady data format there. So this is what we actually apply our CDISC to. So where from we get our CDISC data, there are especially two formats that we have in this pipeline. One are SDTM tables. Those are several tables that hold data by domain. For example, there's one for demographic data and one for all the medications and so on and so forth. And then there are tables that are more flexible, that are especially built for analysis. So those are called the ADAM tables in the CDISC context. And what we've built is an automated data engineering pipeline scheduled every night that built completely on top of open source software, so no strings attached in the sense of lots of so no proprietary software here. And we built this pipeline scheduled every night to transform the raw data in whatever format it's there, some long-term table format, into first those SDTM tables and then specified ADAM tables. There are some that probably always need to be there because those analyses are always need to be done. But we've also defined special tables. I will say something about this on the next slide. That make a lot of standard questions easier to answer, and provide all of these data. So the raw data, as well as the SDTM tables, as well as the ADAM tables for analysis. Right. So, of course, the most difficult or the most work-intensive part of this is to define, okay, which tables should be built? How should they be built? I mean, it's a standard, so there are specifications for how the SDTM tables are built and how the ADAM tables are built, but still this needs to be defined somewhere. And while building this data engineering pipeline, we've developed a domain-specific language for that, that makes it easy to just define variables from the raw data to SDTM and to ADAM files. I have brought one example here that I will show. The important thing here is, I mean, this makes a definition of variables for all of those tables, of course, faster, because you just have to write some lines of not even code. This is also important. It does not require any programming language, so you don't need to know how to program to define this. It's very easy. And it also helps to standardize definitions of those tables over more than one study, because you can just reuse the definitions from one study to the other. Right, so this is the example. This is very generic variables. I only have an example here that builds ADAM variables from SDTM tables. So we name the variable, we say, okay, how should this be displayed in the front end? What is specific to the system here? It says, where does it come from? So which variable is this based on? There may be filters, there may be like in the last variable where we group the BMI variable, there may be groupings like this. There may be small formulas like in defining the BMI variable and so on. Right, and so then on top of this, from all this data, we've built this front end that can do two things that are shown here. Like an example for that. First of all, when you analyze data like this, you need to build a population. So it needs to say, okay, which patients do I want to look at? And which variables for those patients do I want to look at? So this is the first part. You can build populations, and then there can be analyzers built on top of those. There may be more than one analyzers on top of one population, of course. So this is the setup that makes standard analysis easy, because you can have your populations, they can be predefined, and then they can just be analysis run on those. They can be exported, they can be saved, and so on. This is the first example. This is running in production, used by our customer. Right, so the second example I have is a different example. There we already have the data, but we have lots of different data. And we employ different models and different methods, and also some classical AI to do one thing, provide support for clinical documentation. All right, so the problem here is we need in every hospital has to document diagnosis code for every patient, and it's a bad thing if some diagnosis may be overlooked, because this costs money. So also every diagnosis code, of course, that is documented needs to be confirmed. Also, this takes time, and all of this takes time. And yes, sometimes it's prone to errors, because some things are easily overlooked. And the idea is to use different data that a hospital knows about a patient to suggest codes that might be missing, and also help to confirm codes in text passages. Right, so this makes documenting faster and hopefully more effective. And we did, as I already said, different things. So first of all, of course, we have the data that are needed for documentation. So already the documentation data, let's say. And then you can see that there might be some minor diagnoses that coincide with primary diagnosis over and over again. And the idea is, okay, if one of those, if it coincides nearly all the time in our case here means in 95% of all cases, and we have enough cases that this is really significant, then we just suggest this diagnosis. I mean, it may be wrong. This is not an automatism, but the coder is reminded that this diagnosis might be missing. Another thing is going more elaborate and try to get diagnosis from lab results by really seeing, okay, what can we learn of probability of diagnosis given specific results. For this, we also used our dimensionality rejection method, present all the lab results for one patient in one point in a 3D space, and we see that there are clusters, and we see that specific diagnoses are very often in one cluster, so very often documented for the patients in one cluster, so we might suggest those. Then there's a classic AI system that just learns from the knowledge of experienced coders. So coding experts provide rules for coding diagnosis based on lab results. So it's not we are just learning diagnosis from lab results, but we also have rules. So for example, if the calcium values are very high, then there's a diagnosis for this. And the expert provides those rules in a Excel file. Our system translates this file into searchable rules and applicable rules. And then there's an inference engine that uses those specific rules on a specific patient's lab results and suggests the codes that are implicated by the rules but missing in the documentation. The nice thing here is that all the knowledge base of the system can just be updated by updating the Excel file. And then for fourth and last, as I said before, also all those diagnoses need to be confirmed. This often needs lots of long texts to be read, and so we have employed a small probabilistic model, so no deep learning here, that learns words corresponding to diagnosis from a definition knowledge base and other existing files, and then highlights words that might correspond to a diagnosis. So I have just one example here, where we found words that make up the definition of an ICD code in the case file, and then it highlights that, and by that helps or speeds up the process of actually confirming diagnosis for the documentation. Right, and then there's another example. This is more like this was urgent and needed to be done, and we showed that we can do it. Last year, the demand for PCR results surged upwards, unfortunately, and so we got the interesting case of automatic classification of COVID-19 PCR data. Already, I mean, every system that analyzes PCR data usually has some kind of analyzer, but those need to be calibrated, and those need to be taught what to do. And the idea here was that we learn from data that was already classified, so from PCR results that were already classified. We learn to classify them, and also we do it in a way that is highly probable to be transferable to other genes than the ones that were looked at here, and by that transferable to other virus detections, not only COVID-19. Right, so we search for a better solution for automatic PCR results. Of course, it's like there are different assays for different genes, so different viruses, and usual analysis, common analysis solutions need to be tuned and taught for everything of that. So we said, okay, let's use a deep learning model like the one that is sketched out on the right to learn classifying this kind of curves and also make it transferable. Just a few words for that. That's one model developed among others by our founder Sascha Lange. This network is specific, meant for time series data that have channels that are somehow connected to each other. That means that what we learn is not only that there is some, that it's continuous over time, but also that there is some interactions among the different channel of a multivariate time series. In our case, those are 3 genes. And what we see here is, I mean, this is of course not really a time series, because the x-axis in those plots is cycles, not time points. But I mean, the structure of the data is about the same as a time series, because it's something you have. It's an ordered, it's an ordered sequential x-axis and an ordered sequential plot. So we can treat it as a time series, and we did here. And as we can see here, we had very good results, and we showed that this is really optimizable in this way very easily. We had a test set of 900 curves, and actually, when we look at our ROC curves here, we see that on this amount of data, yeah, we do almost everything right, and it's very hard to see how good we really are, because it might be it's too less to have any significant false predictions. It might, and this might all be chance, we don't know, right? So for the first gene, we misclassified actually 1, and we did it in the right direction. So we said it was positive, but it wasn't. So look into it again. For the second gene, we had exactly no misclassifications, and for the internal control, interestingly, we had 2. But so this is really, we did it. Right. And the last example I've got is the one that I already mentioned before, an artificial intelligence to support doctors in deciding if there is atrial fibrillation in an ECG, in a long-term ECG. As you might know, long-term ECGs are running over about 3 days. That's a lot of data. And actually, that's one of the big reasons why it's not possible to just check everyone for atrial fibrillation without any idea that there might be something. But actually, I mean, it would be very helpful, because atrial fibrillation is one major risk factor for stroke. So everything that helps to make that easy might, or easier or faster, might definitely help. So what did we do for that? We again used the same kind of network, but on different data that we used before. This time we had 3-channel long-term ECG data. The interesting thing here is we had data of more than 1,600 patients. What is very much, because the data sets that are usually used by the research papers often have about 30 or 100 patients. And so this is really very big training set. We aimed not for absolute correct, for being absolutely correct, but for do not misclassify atrial fibrillation as okay. Because what we actually do is our doctor gets a screen like this. So this is the interface for the doctor who uses this product to see if there is atrial fibrillation in this long-term ECG. And everything that is marked not green here has a probability bigger than 0 that there might be atrial fibrillation in here. So if the AI misclassifies something as atrial fibrillation, which is not, this will not be a problem, because the doctor will be looking at this point and will just say, okay, this is not something bad. But if it misclassifies something as okay that actually is fibrillation, probably the doctor won't look at this point, because this is exactly the idea of the whole thing, that we mark, our AI marks the places in this long time series where it is worth to look at and look for atrial fibrillation. And the doctor looks through those and then classifies this as atrial fibrillation or not. And the result will be a report that can be exported and sent out. Right, so this is, no, this was not what I wanted to do. This is basically what happens here, a small video of how a doctor could go through this. So this is one point where it looks like there might be something. You can look at single channels and then say, in this case, the doctor says, no, this is okay. There is nothing in here. Right. And this can go into the report. So this thing is actually, I mean, it's made from the small device that you have seen on the first slide, and a lot of software, some software to upload the ECGs, and this software for the doctor. And it's actually a certified medical product, and it's in productive use. Right. So let's jump to the conclusion then. We have seen that we can solve real-life problems in the field of health with machine learning. And also we have seen that they can be, those models can be deployed in productive solutions and even be part of certified medical products. So thank you very much, and I'm looking forward to your questions.
Yes, thanks a lot, Julia, for your amazing presentation. You gave us deep insights of machine learning in the health area. Thanks a lot. And in the chat, there are a lot of questions. I don't know if you see the questions. I can also read it, and you can answer them.
Okay.
The first was, are your usual applications area 4D or less?
Oh, this is an interesting question. I mean, usual application area 4D or less, what does that mean? I mean, we have very different data sets, actually. I mean, we've seen in our medical examples very, very different data sets. So, for example, those genome data, I mean, we interpret it as having 60,000 dimensions or more, right? So it's very high dimensional. On the other hand, I mean, a time series like the ECG data, what is the dimension of that? And today, this is the dimension does not apply here, but there we have 3 channels. Sometimes we have time series with only 1 channel. So I think this depends very much on the application, not so much on. So I can't say my usual data set has this and that many dimensions. I can say that we often have very high dimensional data that then is all those cases for dimensionality reduction, because that helps to look into the data. But in terms of time series, for example, I don't make that many sense of the word of dimension there, and I'd say we also often have data sets that aren't that high dimensional, but of course all those industrial settings where we are confronted with sensors, for example, those are often very many sensors, and by that very many dimensions. Yeah.
Okay, and another question is the project on ECG. Is it also a time series work?
Yeah, definitely. ECG is one, I mean, is a textbook example for a time series, right? So yes, and we also especially used this time series model that I mentioned earlier. I can go back to the slide, perhaps. So wait a moment. I go back here. Yeah, right here. So yes, we used this time series model to do it. I mean, this is comprised of a convolutional neural network part and an LSTM neural network part. Yeah, this is definitely a textbook example for time series, and we also use the time series specific model here.
Okay, there are some technical questions. The underlying database, is it PostgreSQL? And are you using column store at all?
For which of those projects? Yes, we often use Postgres, but we also have data that is not available in a way where it makes sense to use a classical database.
Okay, and there are questions to the Excel. Is Excel a good choice for storing a knowledge base?
Actually, I think that depends on how big this knowledge base is, of course. I mean, this is those rules in this project were about 30 rules. What is something that can be very well stored in Excel? I have another project where we use something very similar, where we have about 60 rules, where I'd say still Excel is quite a good choice for that, because it's I mean this data is so small that it doesn't matter where to store it, and Excel is something everybody of the domain specialists knows and thus can use. So this is just a very good trade-off between storing this and modifying it by non-programmer domain experts, right?
And there's questions about the PCR data classification. Have you checked out other classifiers, and why do CNNs help there? Is that a 2D problem?
Yes, actually, we've checked out other methods. This was part of the POC there, actually. We had 3 different models where we looked at. One is a classic probabilistic classifier. One was a classic machine learning model, like random forests at that. And one was this deep neural network. And actually, they were all quite good because the data is not that complicated. But we were a little bit better than the classic model without excessive tuning. So the classic model can be tuned, of course, and can be very good, but we were a little better than the classic model without excessive tuning with our deep neural network. And then again, the deep neural network makes transfer easier. So if we are about the same, if we get about the same results, we have less tuning and more transferability. That's good. And about the convolutions, that's interesting. I mean, one thing we do is convolutions are not only interesting in spatial dimension, they are also interesting in time dimension, and this is what we're using here. So we also use spatial dimension convolutions when we have multiple channels. This is what I said, why this is specifically good for multivariate time series with connected channels, so where we have an order in the channels, so we can use spatial convolutions too, idea from image processing actually, but we definitely use time convolutions for all those time series models.
Okay, there are 2 last questions, which are nearly the same. Is the diagnosis solution for hospitals still in sort of a development phase, or is it already in the market and used by customers on daily basis? And do you think your solutions can be also used in smaller hospitals today?
This is something we provided as a prototype to the customer to deploy it themselves, and I actually don't know in which state it is at this point. But I think it could be used in smaller hospitals, definitely. But we built it for a customer that is already consulting hospitals, so not as a standalone solution directly marketed to the hospitals. So this is not the exact application area, but of course it could be used there, yeah. And it probably could help because they are not that big and not that strong to have big software solutions on their own, yeah.
Okay, I think we have it. There are no more questions in the chat. Once again, there's just a last question. Okay, I just read it concerning the prediction of the secondary diagnosis, that it's the data for learning came from, where you concerned of introduction bias for diagnosis.
Yeah, this is interesting. We actually discussed this on the project very excessively because yes, it comes, I mean, it's learned from the already existing diagnosis data that is there. And yeah, this bias thing is something we discussed because of course, if you have one hospital that always makes the same mistake will be repeated in such a model, definitely. One solution to that would be if you are not just one hospital but are consulting to many hospitals, you could learn those secondary diagnoses over several hospitals, and by that probably get rid of the bias of only one hospital. And you could even look if your hospital differs or has a bias compared to the whole system. But also, I mean, there is, we talked to the domain experts there, and one thing was that there sometimes are biases that are so widespread that probably such a system will learn them too. But again, the question is, what is the aim of the system? This specific model cannot reduce bias because it just learns the bias as it's there. So it only prevents things that are done wrong sometimes, but not always. And on the other hand, if there's something always coded that's actually not there, but everybody does it wrong, the system will repeat this. But still, it's a support for a real-life process, and it at least doesn't make the process worse. And if you have the possibility to learn over several systems, you might make it better and might see your own bias. So yeah, the aim is not to be perfect, but to speed up the existing process.
There are some further questions. Do you validate your machine learning algorithm? Yes, and if so, under which guidelines, industry regulatories?
This is an extensive question, I'd say. Yes, of course, we validate our algorithms. We are very strict with handling test data, for example. And actually, the regulations differ, right? I mean, there are regulations for our industry projects that I do not know that well. And of course, there are regulations in the certification process of a medical device that require, for example, very sincere separation of training and test data. So we solve this in that way by just not recording the test data before the model existed. There usually it requires at least, I mean, you need to be explainable. That's one thing. And we had, as I mentioned, we had so many more patients in our training data than the usual research papers on those topics, that this was definitely a plus.
And do you use health-related regulation like FDA, EU, or something like that?
I personally did not come into contact with FDA or EU regulations for medical studies, because the thing we built was for a customer who does this, and so they of course have their processes that are done according to those regulations, but this did not apply to us at this point, because we did not do any modeling for them yet, but only provided the system for the underlying data.
There's a further question. A never-ending story is coming up. So here you have you tried unsupervised learning? If so, were you able to see differences between performance compared to supervised learning?
Yeah, on what, I'd say. Yes, of course, we are working a lot with unsupervised learning because oftentimes we do have data where we don't have any useful targets. I mean, for example, the thing I showed you, the 3D representation of the cancer cell mutations. This was a data set without targets. We don't, I mean, we have the cancer, we have the information which cancer the cell is related to, but yeah, this could have been even used for some kind of supervised learning perhaps, but the 3D representation was learned completely unsupervised, and the color overlay is something we did afterwards. So, so to say, to prove that our representation learned something useful. So I'll just share that again. So yeah, we oftentimes use. So here it is. So yeah, we oftentimes use unsupervised learning for different questions. Also the project I mentioned before with the e-mobility charging devices, the first predictive maintenance model was learned unsupervised because we didn't have any useful targets, and we just learned, okay, does this seem unusual that nobody's charging them? And on the other hand, when we have targets, when there is reliable labels for data, supervised learning is used. So it very much depends on the case, it very much depends on the data, and very much depends on can we acquire useful labels somewhere.
Okay, once again, last corner. Is there a last question? If not, once again, thanks a lot, Julia. I think today we have it. The record will be given, I think, tomorrow to the YouTube channel. Thanks a lot. Stay healthy, with or without machine learning, and have a nice evening. Goodbye.
Yeah, thank you very much, and goodbye from me too.